Welcome back, everyone. In this video, we're going to start Chapter 5, looking at molecular composition. We're going to talk about how atoms are organized into molecules, and we have molecular and ionic compounds. We're also going to do some calculations to determine the molecular mass of a compound, and then also determine the mass percent of an element within a compound. So, up to this point, we've only really talked about elements. One atom at a time. So talking about, we talked about the carbon atom or the lithium atom or rubidium. And we talked about how they form ions. But it's only very few elements that exist as atoms only, and those are the noble gases. The vast majority of elements in nature exist in the form of molecules or compounds. For molecules, there are three main types. There are homonuclear diatomic molecules. What that means is that we have two atoms, but they are the same. Homo, they are the same type of atom. Okay? Then we have heteronuclear diatomic molecules. Those are two atoms, but they are different. Hetero. And then we have polyatomic molecules. These are molecules that have the same element, but three or more of them. And so these are our basic types of molecules. And then we can also talk about compounds. Compounds are where we have three or more atoms, and there's at least two different types of atoms. So, for example, we could talk about molecular compounds, including water, methane, or ammonia. These are compounds because there are, in each case, there's at least three atoms. Here we have 1, 2, 3 atoms. Here we have 1, 2, 3, 4, 5. 1, 2, 3, 4. So each has three or more atoms, and each also has at least two different types. So here we have oxygen and hydrogen. Here we have carbon and hydrogen. And here we have nitrogen and hydrogen. Okay? Then we also can get rearrangements of elements into what are called ionic compounds. And the main difference we will see between molecular compounds and ionic compounds is based on the type of bonding that they have. We'll get to bonding in Chapter 6, but we'll look at it very briefly here. Molecular compounds consist of nonmetals that are bound to each other. So remember, when we talked about nonmetals, we described how they are found mostly on the right side of the periodic table. Hydrogen is an exception to that. It's often written on the left side of the periodic table, but it behaves as a nonmetal. And that's because it has a very high ionization energy. So when you have groups of nonmetals together, those form molecular compounds. And going back to the examples that we saw, we had water, we had methane, we had ammonium. You can have other types of molecules as well. There are things like C2F2. This is a freon compound, and this is a molecular compound. So the main point here is that we have nonmetals that are bound to each other. Ionic compounds consist of metal cations bound to nonmetal anions. So you have a combination of a metal with a nonmetal. And metals are found mostly on the left side of the periodic table. There's one exception that you need to be familiar with in terms of forming ionic compounds, and that is the ammonium ion is a cation, so it behaves like a metal when it forms compounds. So other examples of ionic compounds would be calcium chloride. We have the calcium cation with the chloride anion. We could have maybe rubidium oxide. That's an ionic compound. Or, as we said before, ammonium. So if you have ammonium with nitrate, that's a combination of the cation ammonium with other nonmetals. And so that will form an ionic compound. So each molecule, whether it is a molecular compound or an ionic compound, we have a chemical formula, and that's what we've been representing them so far. And there's different ways to represent chemical formulas for molecular compounds, and that is that we can use the empirical formula or the molecular formula or a structural formula. So the empirical formula gives us the ratio, the relative ratio of each kind of atom within a substance, and this is the smallest integer ratio. So, for example, we could give CH2O. This we cannot reduce this ratio any farther because that would then get us C1/2 HO1/2. So we want the smallest whole number ratio. However, CH2O we could write in a variety of different combinations, meaning we could have C2H4O, C3H6O, etc. So those those ratios that are not the smallest whole number ratios, those are the molecular formulas, and they represent actual molecules. So another example of that would be C5H10O5. And the actual molecule of this could be our ribose. So the structural formula shows us how these elements are bound together to form the various molecules. And something that's important to note is that ionic compounds, these don't have a molecular structural formula in the same sense, because these form extended networks that are three-dimensional in shape, and so we don't distinguish between the empirical formula and a molecular formula because we're only ever looking at that ratio, that lowest whole number ratio, and then it replicates itself over really thousands and millions of copies. So you would never see something like Ca2O2. You always reduce down to the lowest whole number ratio when it comes to ionic compounds. So how do we, let's talk more about the chemical formulas and determining the molecular formula of a molecule. So the molecular weight, or the formula weight, is where you take each individual atomic mass and you sum them up. This uses the masses that we find on the periodic table. And you can do it both in terms of AMU or in terms of grams per mole. So going back to ribose, if we wanted to find the molecular weight of ribose, what we would do is we would find the sum of the atomic weights of each element. So for carbon, for example, what we would do is take the number of carbon atoms, which is 5, times the molar mass, or the atomic mass of carbon in grams per mole. We multiply 5 carbons times the mass per carbon, and we get 60.05 grams of carbon, and that's per mole of ribose. Look at hydrogen. There are 10 hydrogen atoms. Each one weighs 1.01 grams, and so that gets us 11.11 grams of hydrogen per mole of ribose. Then oxygen, there are 5 oxygens, each one weighing 16 grams per mole, giving us a total of 80 grams of hydrogen. So the total mass of ribose would be the sum of each of those components. We've already talked about how to convert between molar mass and Avogadro, or how to convert between moles and grams and moles and particles. So this is just a friendly reminder that you need to be able to do this in order to continue moving on in Chem 110. So we can use the molar mass to convert between grams and moles, and we use Avogadro's number to convert between moles and the number of that particle. We're now ready to talk about percent composition of an element. So thinking back on ribose, where we had C5H10O5. We might say, what is the percent what percentage does carbon make up of the entire molecular weight? So if we know either the empirical or molecular formula of a compound, we can find the mass percent of each element. And it's fairly intuitive. You take the number of atoms of a given element times the weight of that element over the total weight. So that's going to find us then what is the mass percent of a given element. We can also find the mass percent if you already know what the mass of a given element is of the total. And so this top portion, multiplying the number of an element times its atomic weight, gets you the mass of that element in the sample. And so the mass percent of an element is essentially what fraction or what percentage of the total it contributes. And it's very important to note that the mass percent of all of the elements within a compound must add up to be 100%. So let's do a practice problem. Let's say I wanted to find the percent composition of nitrogen within ammonium nitrate. How might I do this? Well, we've defined the mass percent of an element as equal to the number of atoms of that element times its atomic weight over the total molecular weight times 100%. So the mass percent then of nitrogen would be equal to 2 nitrogen atoms times the atomic weight of nitrogen divided by the total molecular weight of the compound. And remember, the way you figure that out is by adding together the atomic weights of all of the elements together. You multiply by 100% and we see that we have 35% nitrogen. If we repeat this process for each of the other elements, we would get 5% of hydrogen and 60% of oxygen. And thankfully, our total adds up to be 100%. Okay? Here's another way of looking at it, and I want you to try this one. Go ahead and pause the video and read over this on your own to see if you can figure out the solution to this. Welcome back. So, how do we determine the percent composition of oxygen within this compound? Well, remember that the mass percent of any given element is equal to the ratio of that element's mass over the total mass times 100%. Since we know that the oxygen makes up 28.9 grams of the total, and the total mass is 54.3 grams, we can take the ratio of those two and multiply by 100% to get the percent mass of oxygen. All right, here's one last problem. This one is a little bit more difficult. So let's see if you can combine what you've learned into this problem. So go ahead and pause the video and try this one on your own. Welcome back. So we want to know how many grams of carbon are there when we have 24.35 grams of sucrose. Okay, how are we going to think about this? Well, remember that when we talked about the ratio of one element in the total compound in terms of the mass percent. So if we can determine the mass percent of carbon in the total, and then multiply that mass percent by the total mass, then that will tell us how many grams of carbon there are in the total sample. So mass percent of an element is the number of atoms of that element in the compound times their atomic mass divided by the molecular weight of the full compound. The molecular weight is going to be the sum of the contribution from carbon plus the sum of the contribution from hydrogen plus that of oxygen. And again, these numbers come from the periodic table. And these numbers are based on the subscripts within the compound. That gets us a total mass of 342 grams per mole. To find the mass percent of carbon, we'll take the contribution of carbon divided by the total mass times 100%. And that gets us a mass percent of 42.11% of carbon. So 42.11% of this 24.35 grams is carbon. So when we multiply that percentage times the mass, that gets us the mass of carbon within our sample. Okay, that's it for this video. Thanks for watching. Have a great day.